Math 1314 and Math 1324, which are presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, or so others who may have missed it, the ones that have missed today's events can come back and watch it. So now at this time, please make sure that your mics are off for best experience. Otherwise, the feedback could interfere with information we will be sharing. If you are here for the Math 1324, we will be posting the room link on the chat so that you may connect to Math 1324. We'll also be sending individual messages to everyone so that we can gather your student ID numbers to sign you in. And now, without further ado, I'll pass it over to the presenters so that they may begin.
Thank you so much, and good morning, everyone. Thank you for joining us for another session of the Math Happy Hour on Fridays. Welcome aboard. And as mentioned, if you are here to go over 1324, the link is already there in the chat. Please go ahead and click on that link, and you will be transferred over to the Math 1324. So we'll give a few seconds for those of you who are going to join the 1324 room. So the remaining of us that are here, we're going to go ahead and get started with the 1314 math, which is today's session is synthetic division and complex numbers. Okay, so let's go ahead and get started. So first, hopefully you are all familiar with this. The previous section before the synthetic division, we all dealt with polynomials. So we have here a function here, which is a polynomial. We see that it's a degree 3 polynomial, and we know some specifics from the previous section on how to attempt to graph it. But we've also noticed that if we were to be able to be given the polynomial in its factored form, it would really be easy for us to find on the graph where the graph crosses the x-axis so we can better graph it, right? And the most obvious one is this one right here, the x minus 2. We know that if x is equal to 2, we're going to get a 0. That means that the graph is going to cross here at this point to 0. Now for the other ones, we could also see that we would have a 1/2 as an intercept, and then also leaves 2/3 as a x-intercept. But again, if we were to be able to factor it, okay, we would see where the graph crosses the x-axis. And sometimes this could be difficult for us to factor, especially a polynomial that's degree 3 or even higher. So what's going to come to our help is this notion of division, polynomial division or synthetic division. So the first one that I want to start with is this polynomial division. And another word for polynomial division is the word long division. So long division is used to divide two polynomials, and it will help us simplify a large polynomial into smaller chunks or into its factors. Now, there are several things that we need to know. When we are going to be doing long division, the first thing that we need to do is we need to arrange the divisor, okay, and that's the one that we're going to divide into. It has to be arranged in descending order from powers. What does that mean? That the highest exponent has to be the first, and all of the terms after that polynomial have to be in decreasing order, okay? The other thing that we need to also keep in mind is that our first term, our term that we're going to be dividing into our dividend is called our divisor, and the result when we do the division, the answer is called the quotient. Okay, so these are just some basic terminologies. To do division, okay, just to do a quick recap, you're going to do division just the normal way that you do division with if it were just numbers, not polynomials. Okay, we need to multiply a number to our divisor that's going to become close to the first term in our dividend, or the exact same term. And then once we have that, then we're going to subtract. and then we bring down the following term, and then we do the process over and over. We're going to multiply until we've reached all of the terms. So the best way to see this is with an example, yes? But then again, the breakdown is this, that when we divide a polynomial, we're going to make this polynomial simpler. And technically, what we want to do is we want to get the factors of our large polynomial in order for us to find out what the intercepts are. It's for us to better understand the graph or to graph our polynomial. Okay. Now, also the last number here, number 7, says that if there's no remainder, that means that our divisor that we used and our quotient are perfect factors of our long polynomial. Means those are going to be our zeros for our polynomial. Okay, so let's go ahead and get started just so you can see an example. So here we see that we're going to divide two polynomials. So the one on the left is my dividend. This is the one that we're going to divide into. The one on the right here, the 4x minus 3, that's called my divisor. Okay. Now, again, what I'm going to do is I'm going to do it old-fashioned, the way we did regular number division. What I want to do is I want to create this little house, right? And inside my little house, I'm going to put in my divisor. And excuse me, my dividend. And what I want to do is I want to make sure that my dividend is in descending order. Okay, so I see that my degree here of this polynomial is a degree 3. So all of the terms after it have to be smaller. So I do have an x squared, an x to the 1 power, and then the minus 6 is a constant. So I don't have to worry about the order, and I don't have to worry about any missing terms. And we'll cover when we have missing terms. Okay, but let's go ahead and start with this example first. So my divisor here is 4x minus 3, and when I want to divide 4x minus 3 into this polynomial. So what I'm going to do is I'm going to say, what can I multiply to 4x that will give me a 20x cubed, this first term? I want to come close to it. Now, when we were doing division, sometimes we can come to the exact number, sometimes we would come close. But when we're doing polynomials, we can get the exact value. So if you're not coming up with the exact value, then we need to try another number, but we will always get to the exact number. So I say to myself, what can I multiply to 4x to get a 20x cubed? Okay, so let's start with the number. What can I multiply to 4 to get 20? Well, I can multiply a 5. 5 times 4 will be 20. And what can I multiply to x to get an x cubed? Well, then that would be an x squared. An x squared times an x will give me an x cubed. So that's what I'm going to multiply with. And again, so I'm going to multiply a 5x squared. And then again, if you didn't see it, if you didn't see this process visually, you can also do it mathematically. You get the 20x cubed and you divide by 4x, and you would see that you get a 5x squared. So that's going to be my first value of my answer, which is my quotient, to multiply the polynomial. Okay, so then I'm going to put my 5x squared on top of the house, and then I'm going to multiply 5x squared times the 4x. That's going to give me my 20x cubed. 5x squared times the negative 3. That's going to give me my minus 15x squared. But then what follows after division? Well, we have to subtract. Now we have to be careful because we are subtracting polynomials, and we're not just subtracting one number. So then that's why I put a little parentheses here in blue, because this subtraction, in order for me to do the subtraction or the operation, I need to distribute my negative symbol, my subtraction symbol. So before I can do the subtraction, I'm going to distribute. So what that means is I'm going to distribute this negative to the 20x cubed, which is going to give me negative 20x cubed. A negative times a negative 15x squared is going to give me a positive 15x squared. And now I can add. So what I'm going to do is I'm going to go ahead and add. 20x cubed minus 20x cubed is 0. We have a minus 35x squared plus 15x squared is a negative 20x squared. And then I need to bring down my next term. My next term is 23x. So I have to do the same thing again. I need to find out a number that I can multiply to 4x that is going to give me negative 20x squared. And hopefully you can see that if I multiply 5 times 4, again, or a negative 5 times 4 is going to give me the negative 20. And if I multiply x times x, that's going to give me my x squared. So the next term in my quotient is that negative 5x. So I'm going to put it next to my 5x squared here. So I have minus 5x, and I'm going to do the same process again. I'm going to multiply negative 5x to my polynomial. So we have negative 5x times 4x is a negative 20x squared. A negative 5x times a negative 3 is going to give me a positive 15x. But then I subtract, and I'm going to do it again. Since I'm subtracting in polynomials, I need to distribute that negative symbol. So when I do that, it's going to give me a negative times a negative 20 gives me a positive 20x squared. A negative times a positive 15x gives me a negative 15x. So now I'm going to add negative 20x squared plus 20x squared is 0. Then we have 23x minus 15x is going to give me an 8x. Then I bring down my last term, the negative 6. All right. Then now I say to myself, what can I multiply to 4x to get a 8x? Okay, so that value is 2. If I multiply 2 times 4, that gives me the 8. And then I'm not multiplying any x, so the x stays the same. So it's 2 times 4x is a positive 4x. 2 times a negative 3 is a negative 6. But then I'm going to subtract. I'll distribute the negative symbol. So a negative times a positive 8x gives me a negative 8x. A negative times a negative 6 is going to give me a positive 6. So now I can add. And when I add these two, 8x minus 8x is 0, minus 6 plus 6 is 0. So in this particular division, the fact that I have 0 here, this guy is called my remainder. Whatever's left over is our remainder. And this one, we love to have zeros on the remainder because now what I know is that 4x minus 3 was a factor of this long polynomial. Okay, so this is how we do long division, okay, or polynomial division. Let's go ahead and review our terms. It's good to know them, okay? So again, the number that I was dividing with, this is called my divisor, okay? The number inside my little house is called my dividend, okay? The answer that I got outside, that's our quotient, a result of our division. And then again, any numbers left over, this is called our remainder, okay? So let's go ahead and look at something else. In our homework, sometimes we're going to have a remainder, and the remainder we need to put it in this format. We're going to have our quotient, but then we're going to add the remainder, and the way that we add the remainder is going to be the remainder divided by our divisor. So as an example, if the computer wanted me to put it in complete format, the format would be like this. It would be the 5x squared minus 5x plus 2, but since I didn't have a remainder, I would do plus 0, that was my remainder, over my divisor, which was the 4x minus 3. And we all know that 0 divided by 4x minus 3 is 0, so it doesn't really change the problem if we put it in its full term. Okay, but let's keep this in mind because we may have to use this format in order to answer some of our homework problems. So let's go ahead and switch over then to synthetic division. So synthetic division is another way to do polynomial division, but is a lot faster. Since we know that a polynomial is going to be in order, then we can omit some stuff. But in order for us to omit some stuff, the first thing that we need to do is we need to know what our divisor is going to be. Okay, and for us to use synthetic division, our divisor always has to be in this form, in the x minus c. If we have a divisor that has a ax, we cannot use synthetic division for that. Or if it has a square, the x has a square, our divisor has a square, then we cannot use synthetic division. Now, so in short, when we're dividing with synthetic division, we're only using a linear factor to use synthetic division. So let me go ahead and explain to you what this means. Okay, so let's say that we have here our dividend is ax cubed plus bx squared plus cx plus d, and our divisor is the x minus k. So our term, our factor term that we want to use is this k value. okay? So we'll be dividing by k. Now, since we know that our polynomial is in order, and the order means that the degree of each term holds a placement value, I can omit writing the x's and just put the coefficients of all of those terms. So hence here, I would put a, b, c, and d. Okay, these are my coefficients. All right, so to do synthetic division, the way I like to differentiate the long division from synthetic division. In my long division, I had a house that the roof was on top. Now to do synthetic division, which is something similar but different, now I do a house again, but my roof now is the floor. It's flipped. Okay, and then again, I'm not using the x values. I'm trying to make my life simple. And you're gonna see you're gonna love synthetic division. Instead of doing division in, as you saw, 4 or 5 lines, we can do the division just in one line. Okay, so this is the process. What we're going to do is we're going to divide by our k value. And the first thing that we're going to do is we're going to bring down our a value, our coefficient of the a value. And then I'm going to multiply the k times a. Okay, the k times a, once I multiply it, I'm going to put it here. And then I'm going to do the addition of these two coefficients, the b and the k times a. So I'll add those two. Once I add them, the b plus k times a, I'm going to multiply it again. I'm going to multiply k times this term, and then I'm going to put it here on below the c, and I'm going to do the same process. I'm going to add that term and add c to it, and then do the process again. I'm going to multiply k times that term, and then put it here below the d, and then since d is my last term, it will be my last addition. I'll add the product of that, and it will go here. And again, remember, this last value will be our remainder. And we're going to be super happy if it's 0. And if it's not 0, then it's okay. Okay, we just know that the k was not a full factor of that polynomial. All right, so let's go ahead and do an example. Like I said, these are my coefficients. The last the value here in the blue R is my remainder, and these are the coefficients of my quotient. And I can also convert it back into its original polynomial, and you'll see that. Okay. All right. So let's go ahead and do synthetic division to divide this polynomial. Now my polynomial, this is a simple polynomial. We have x squared plus 5x plus 6, and my divisor is going to be x minus 1. So as you can see, I can use synthetic division because I have a linear factor. Okay, so what is my k? So if you don't see it, again, this is the factor polynomial, but the factor term is solving for x. So our k value is going to be a positive 1. Think of moving that negative 1 to the other side of the equation and solving for x, okay? So my k value is going to be 1. Then the next process is to list only the coefficients. We're not going to write any variables. We're just going to write the coefficients, but we got to make sure that our coefficients are in order. So we do have them in order because our degree of our polynomial is degree 2. The next one is 1, and then our constant. So we can go ahead and put our coefficients, which are 1. We don't write a 1 here, but we know that there's a 1, x squared, the 5, and then the 6. Okay, we're going to get started. Let's bring down the 1. We bring down the 1, and then I'm going to multiply 1 times 1. When I multiply 1 times 1, that gives me 1, and I'm going to put it right below the 5. It's the next step, okay? Then I'm going to do addition. 5 plus 1 is 6, and then I do the process again. I'm going to multiply 1 times 6, and 1 times 6 is 6, and then I'm going to add again. 6 plus 6 is 12, okay? So if we can see here, this 12 is my remainder, okay? Now, if I wanted to rewrite this, again, this was my dividend, the x squared plus 5x plus 6. Now, my quotient here is this, the 1, 6, 12, the full, right? But keep in mind, when we divide, dividing means we make simpler. So with this division, we're going to decrease our dividend by 1 degree. So if we started with x squared, my quotient here is going to be 1 degree less than my dividend. So if I write this here, this 1 refers to just the x, no longer x squared, but just the 1. And then the one that follows next would be my constant, the 6, so it'd be plus 6. And the way that I write it on the computer, the way the computer wants me to see this remainder is plus 12, the remainder, over my dividend, which my divisor, excuse me, which was x minus 1. Okay, we always want to write this, especially in the computer, they want to write it as in this format. All right, so let's go ahead and do another one using synthetic division. Okay, again, my divisor is x minus 8. I see that this is a linear factor. I can use synthetic division. All right, so the $1,000,000 question will always be, what is my k? What is the factor that I'm going to be dividing with? So again, you can solve for the x, and we see that our k value is going to be a positive 8. So that's going to be our dividing factor. Now, our dividend goes inside my house, or my upside down house, but I got to make sure, is it in order, and do I have all terms accountable? The answer is yes. I have a cube, square, 1, constant. So let's write only my coefficients. So I'm going to write the list of the coefficients are going to be 4, 36, 36, and negative 32. So let's go ahead and do it. Let's go ahead and do synthetic division. The first thing, bring down the 4, multiply 8 times 4. That's going to give me 32. Add 36 plus 32. That gives me 68. Let's go ahead and do the process again. Multiply 8 times 68. That gives me 544. Let me add 36 plus 544. OMG. This gives me 580. And then let me do the process again. I'm going to multiply 8 times 580. And that's going to give me 4,640. And then I'm going to add that to the negative 32. This is going to give me 4608. So again, just as before, the 4608 was my remainder. My quotient is all of this, the 4, the 68, 580, and the 4608, but the 4608 was part of the remainder. So if I rewrite the answer as a polynomial, again, I started with a cube. My dividend was a cube, so my quotient is going to be 1 degree less than this. So it's going to be 4x squared plus 68x plus 580, excuse me, plus my remainder, which is written as 4608 divided by my divisor, which is the x minus 8. Okay, so hopefully you see that we love synthetic division. We could do division in one line. Very quick process. Okay, so let's try one more. Let's do synthetic division again. For this one, we know we can do synthetic division because we do have a linear factor that's being divided to this polynomial. But then we noticed something different than from the ones that we had done before. The ones that we had done before were x minus a number, and the number that we were dividing was a positive. Well, again, I told you why it was positive, because we were for that x. So to solve for the x, I have to move the 7 to the other side of the equation. That's going to give me a negative 7. And that's one way to think about it. But another way to think about what the k value is here. The formula that we said that we needed to have to divide using synthetic division is in this format, x minus k. And if we have a positive here, the only way that this became positive from our formula is if that 7 was a negative 7. And if I put in here the k as negative 7, negative 7 times a negative sign is going to give me this positive 7. So hopefully you see these are two ways to know for sure what the k value that you're dividing. You can either solve for it as an equation, or just know that because the formula is x minus k, if this becomes positive, then that means my k value has to be negative. Okay, so then on this problem, my k is negative 7. Now what's going to go in here is only the coefficients of my dividend. But if you notice something here, the computer tried to trick us. They changed the order here. So we need to put it in order before we do our division. Okay, so this 2x cubed, the 3 is my highest degree, so that one goes first. That one's correct. But the one that should go next is the positive 21x squared. followed by the negative 6x, and then the last one is my constant, the negative 42. Now it's in order, so now I can continue with my synthetic division. So the first coefficient is 3, 21, negative 6, negative 42. Let's go ahead and do it. Let's bring down our 3, multiply negative 7 times 3 is going to give me a negative 21. 21 minus 21, that's 0. No worries. I'm going to multiply negative 7 times 0. That's going to give me 0. I'm going to add negative 6 plus 0. That's going to give me a negative 6. Now I'm going to multiply a negative 7 with a negative 6, which is going to give me a positive 42. And when I subtract negative 42 plus 42, I get 0. Awesome. We love it when we have zeros because what that tells us is that x plus 7 is a complete factor of this polynomial, okay? So let's go ahead and write our quotient. So our quotient is 3x squared. There was no x value, so that's 0x minus 6 plus my remainder. Again, my remainder was 0, 0 over x plus 7, and the computer is very happy on putting just the answer like this. Since 0 times x is just 0, and 0 divided by anything is 0, our answer is 3x squared minus 6, okay? So this is our presentation on synthetic and long division. So, but let's do one more. Let's practice one more, okay? And this one's a little tricky as well, okay? So first, what do we need to find out? What is our k value, right? So here, if we see that our k value is going to be a positive 5 because it's in the format of x minus k. So our k is a positive 5. Or if you wanted to solve it as an equation, you move the negative 5 to the other side of the equation, gives you the positive, okay? But then we see also something different on this one. If we have our dividend here, it's missing a term. It's missing the x to the first power term. So in order to compensate that, because the order matters, the placement value matters when we're dividing. Think of numbers. If we forget a 0 in the placement value, we might not end up with the correct value. So we need to account for placement values. So in order to fix this, that we're missing the x to the 1 power, we're going to add a 0x. And again, our 0x is our placeholder. It's going to make sure that we have the right order and placement and value for all of our terms. So let's go ahead and do our synthetic division. So we know that our k value is a positive 5. And what's going to go in here is only our coefficients. Let's go ahead and put them on. So we have a 1, a negative 3, the 0, and the 6 from our constant. Okay, so now we can go ahead and start. Let's bring down our 1. 5 times 1 is 5. So, which is 5. Negative 3 plus 5 is 2. 5 times 2 is 10. 0 plus 10 is 10. 5 times 10 is 50. And 6 plus 50 is 56. Okay, so now our remainder is 56. It wasn't 0. It's okay. So let's go ahead and write our quotient. Our quotient is 1 degree less than our dividend. So it's x squared, 1x squared, plus 2x, plus 10, which is my constant, plus the remainder, which is 56 divided over my divisor, the x minus 5. Okay. So again, this synthetic division is a quick way to simplify a polynomial and find the factors. And again, we love it if the remainder was 0, because what we would discover is that we have the factors in order to find the x-intercepts. Now, let me show you another way that we can find out if the factors are factors of the polynomial. And again, this is called, this new method is called the remainder theorem. And the remainder theorem says this, that if I get that k value and put it into my function, that's going to give me the remainder. Now, we know that if the remainder is going to be a number, then that means that k value is not a full factor of that polynomial. But if we have a result of 0, then we know that that factor is a full factor of our polynomial. Now, let me do it with an example so you can see what I mean. Okay, I'm going to use the remainder theorem and also synthetic division to find each function value. So what I want to find out is if k is a factor of 2x cubed minus 7x plus 2. And what the remainder theorem says is that I'm going to plug in that value into the polynomial. But first, let me go ahead and do synthetic division to show you that it's not a factor. Okay, so if I divide by 1 to this polynomial and do synthetic division, again, through the process, you'll see that my remainder is -3. And check it out. Check it out what the solution gives me when I plug in this factor of 1 back into my polynomial. So we see that x equals -3 is not a zero, the polynomial, but let me use my remainder theorem. If I plug in 1 to this polynomial, 2x cubed minus 7x plus 2, everywhere I see x, I'm going to plug in that 1. So 1 cubed is 1, 2 times 1, and then we have a 1 times a 7 is a -7, the plus 2. Okay, so then 2 times 1 is 2, minus 7 plus 2. 2 minus 7 is -5. -5 plus 2 is a -3. So you see here, the remainder theorem, when I plug in my k term, it's going to give me the remainder that I would get if I would have used synthetic division. And again, the reason why we would want to use the remainder theorem is for us to not find the polynomial, not find the quotient, but to find out if that k value is a zero of the polynomial. Yes, it's if it's an x-intercept. So that's why we would want to use it to quickly find if the value is a zero. Okay, so let's go ahead and do B part. Let's see if -2 is a zero of this polynomial. And first I'm going to show you with synthetic division. If I do synthetic division with using k as -2, I am going to see that, oh, I am going to get a zero. So then what that means is that -2 is a zero of the polynomial, is a factor of the polynomial, okay? So it's one of the places where my polynomial is going to cross the x-axis. Again, by now, hopefully we know that when we're talking about zeros, we're talking about the intercepts of the x-intercepts of the graph, yes? So let's go ahead and use my remainder theorem to prove that -2, in fact, gave me a zero as a remainder. So again, I have my polynomial 2x cubed minus 7x plus 2, and everywhere I see x, I'm going to plug in -2. All right. So again, for those of you who are Math 1324, the link is on your chat. If you just look at the chat, you can link on it. But if my facilitators, if you mind putting back in, there it is. The link is back there. Okay. All right. So if you see here that when I plugged in the -2, my solution, my answer was 0. Okay, you're welcome. So again, the remainder theorem, we don't want to use it if we want to find the quotient, okay? But if we ever want to just a quick way to find if our factors are zeros of the polynomial, then we would use our remainder theorem. Easy, quick way, but I don't know. I don't know about you, but I think the synthetic division is also a quick way to find the zeros, which is equally the same as the remainder theorem. But again, that's just my opinion. All right, so um, let's look at and see how synthetic division helps us solve equations or find the zeros or find the intercepts of a function. So if I say that the x equals -2 is a zero of 2x cubed minus 7x, oh, the way it helps me is that I know from my past work is that this is a cubic function, and this cubic function at most is going to have 3 zeros. So I'm missing 2, but they gave me 1. They say that x equals -2 is a 0, but I know that technically this polynomial or this function should have at least 2 more zeros. Okay, so how will the synthetic division help us? Well, we saw that -2 was a zero of the polynomial because when I did the synthetic division, my remainder was 0. okay? But the big help comes by doing the synthetic division, that my quotient is in the form now 2x squared minus 4x plus 1. And now, instead of having to try to factor a cube polynomial, we have a lot of stuff under our belt, or we have some arsenal that would help us factor 2x squared minus 4x plus 1. And again, there's several techniques that we can use when we're dealing with quadratics. This is a quadratic, and we can either factor it, we can complete the square, we can use square root property, or we can use our quadratic formula to find the zeros. Okay, so that this is how synthetic division is going to help us. It's going to help us make that polynomial, our dividend polynomial, smaller into something that we can work with. So if you see here, I always like to, my first approach to solve a quadratic is to factor it. So I see that 2x squared minus 4x plus 1 is factorable by using my factoring by grouping. And I see that it can factor by 2x minus 1 times 2x minus 1. This guy's a perfect square, okay? So if I were to solve for x for both of these, again, if you see here, I would add 1 on both sides and divide by 2, okay? X is equal to 1/2. So we know what's happening on this graph. We covered this when we were doing polynomials, that when we have multiples, okay, our multiplicity of our zero is more than 1, then that means that our graph is going to touch at this value, that it's not going to cross, it's just going to touch our graph, okay? So again, this is how it helps us, how synthetic division helps us graph and solve polynomials. And we know by knowing the zeros. The zeros for this polynomial, as mentioned, it does have 3. It has a -2, and the 1/2 counts as a double. So these are my 3 zeros, okay? So this is how synthetic division helps us solve equations. So let's go ahead and go to our next subject, okay? Jumping to our new material is this notion of complex numbers, okay? So unfortunately, we're gonna make some of our students sad with complex numbers, because up till now, when you were solving for this equation, x squared plus 1, and we said, okay, find the zeros for us. So when you did the math, you subtracted 1 on both sides, you use your square root property to solve for x, and then you saw, oh, square root of -1 has no real solution. So up till now, on your homework, you were just putting that, oh, they don't exist. That means that we knew that if we had solving for x gave us a negative inside the radical, we knew that there was no x-intercepts. But really, what the true answer is that there's no real solutions. And that's fine, but what we want to do, and the reason why I say that we're going to make you sad, is because, yes, in fact, when we're solving and we have the negative number inside, what it's telling us is that our parabola is not crossing the x-axis. Either the parabola got shifted up, that it made the parabola not cross the x-axis, or the parabola was flipped and then shifted down, and it's not crossing our x-axis. And this is our x-axis here, this is our x-axis here. And this was a telltale sign that, hey, our graph does not cross the x-axis, yes? But it may not give us a real solution, but the square root of a -1 does give us some value. And this value, we call this an imaginary value, okay? So when we take the square root of -1, this is going to give us an imaginary unit. And we represent this imaginary unit because it's imaginary. Square root of -1, we're just going to say that it's going to be I for imaginary. And a good thing to know is that if I ever would have to square I squared is going to give me -1. And then we can see it here. If I have the square root of -1 and I square it, I know that the exponent is going to be 1, and it's just going to give me that -1. So this is going to be useful information later on, okay? So the square root of I is going to be -1. Now, this is what's called a complex or an imaginary number. But what is a complex number? A complex number is something that it has a real part and an imaginary part. And the standard form of a complex number is given by this, a plus bi, where A is going to be my real part and BI is going to be my imaginary part. Okay? So again, this is the definition that the book gives you that I just explained. Okay? A complex number in standard form is in A plus BI. This is what it means to be a complex number. It doesn't mean it's a hard number. It just has a real part and imaginary part. The A is the real, the B or the B with I is my imaginary part. Okay? So let's do simple operations or basic math operations with complex numbers. Let's start with the easy one, or the two easy ones, the sum and difference, okay? So to add two complex numbers together, super easy. The way you do this is you're just going to add real part with real part and imaginary part with imaginary part. That's how we do the sum of complex numbers. And you see it here with the formula that the book gives us. If I want to add this complex number with this complex number, what the addition is going to be just the real parts. The A and the C are the real parts, and I'm going to add those together, and I'm going to add them with only the imaginary parts. The imaginary parts here are the B and D, the B and D, and we factor out the I. But this is so you can see that we're going to be adding real with real, imaginary with imaginary. Inversely, also the subtraction works the same way. If I have two complex numbers, in order for me to do the subtraction, okay, the way you do it is you're going to subtract the real with real, and you're going to subtract the imaginary with imaginary. Okay, so the best way to see these is with an example. Okay, so let's do these A, B, and C. Let's start with A. A is 3 plus I is my first complex number, and I'm going to add it to the second complex number, which is 6 plus 5I. Okay, so here, using the definition, here the first one, and it doesn't matter which one is first, okay? I could have flipped it, but it doesn't matter, okay? So here, in this case, my 3 would be my A. Here, my B would be 1 for the first complex number. In the second complex number, the C would be the 6, and the D would be the positive 5. So in order for me to add these two complex numbers, I would add the real with real, imaginary with imaginary. So it would be the 3 plus 6 and the 1 plus 5. And my result would be here. 3 plus 6 is the 9. The 1 plus 5 is the 6i. And this is how we want to write our answers in standard form. Please keep this order. You're always going to put the real number first and then the imaginary. Okay, so this is standard. Imaginary, real plus imaginary. Okay, so hopefully you see these are very easy. Let's go ahead and do the next one. So let's perform. Let's see here. Did I skip? Where's my B? Oh, my B was a subtraction. Okay, never mind. So thought they were all addition. All right. So here we go. Let's do B. This is B. Now we're doing a subtraction. So here we're going to use the definition that the book gives us to subtract these two terms. The first complex number is 3 minus I, and I'm going to subtract it with this other complex number, 2 minus I. So again, just replacing what's real with real and what's imaginary with imaginary. My real parts are 3 minus 2, and I'm going to subtract my imaginary, which is a negative 1 minus a minus 1, right? So here, 3 minus 2 is 1. Negative times a negative is a positive, so negative 1 plus 1 is going to give me my 0i. Now, just be careful, depending on your instructor, if they ask you that all answers have to be in standard form, don't forget to write the 0i. Okay, the 1 plus 0i is the standard form of this complex subtraction. But again, on the computer, I don't think it will care. I think the computer, if you just write 1, the real part that was left over, it will take it, okay? So that's our answer. Our answer, the subtraction of these two complex numbers, is just a real number 1. The imaginary numbers cancel out, okay? So let's go ahead and do C. Oh no, C is a little bit different. I don't see an imaginary number there, but I love this problem because this one is actually having me to do a little extra work, because even though I don't see an I here, there is an I, because all I have to do is I see that there's a negative inside this radical. Okay, so I know that this number is going to produce, or the square root of this number is going to produce an imaginary value. All right, so let's go ahead and do this. How do I fix this? Okay, so one of the things that I like to do is first I can write the solution. Okay, the solution would be real plus real, imaginary plus imaginary. Okay, so here we have the real plus real. So we have the -3. We would add it to the +5, and then the imaginary part would be our square root of -8 plus the square root minus the square root of 56. Okay, but what I would like to do is separate what's inside my radical into a product where I can see the formula for the I. Okay, so if I have this inside my radical, if I convert the square root of -8 into this product, -1 times 8, that gives me -8. But I know that the square root of -1 produces an I. And then I'll do the same thing for the -56. I'll separate it into a product of -1 times 56 because I know that the square root of -1 is I. Okay, so if I rewrite this, I see that I have inside the square root of -1 inside, okay, which is the I squared, or you can we call this value the I squared, which is going to just become 1, the -1 outside. Same thing with this one. This one's going to become -1. So if I simplify it to what this means, again, I have this. This is now my terms. I have the -3 plus 5 was the 2, but now I have an addition of two complex numbers. I can, but I see that in order for me to add the complex numbers, I have to have the same radical. And the way they're right now doesn't look like they are the same. But let's see, can we simplify this even further? So the 8, I know I can take the square root of 8 by simplifying it by doing 4 times 2. Okay, and I know that the square root of 4 is 2. Okay, same thing with the 56. I know I can simplify this by multiplying 4 times 14. And I wanted to multiply by a 4 because I know that the square root of 4 is 2. So when I do this, it has me simplified this. Okay, so I now, if you see here, I have a 2i plus square root of 2 minus 2i plus 14. This will be my answer. I cannot go any further. I cannot combine them because these are not like terms. Okay. And then right now, with the next example, I'll show you another way. If you don't see these products, I'll show you another way on how to solve these. Okay. But this would be my answer. This would be a kind of a complicated, since I cannot add these two radicals. In order for me to been able to add these two radicals, they had to have the same square root value inside. Okay. Since they're not, I'm just gonna leave them alone. Okay. All right. So let's do let's do a product. Okay, so these first two examples were adding and subtracting complex numbers. Now let's go ahead and do a next basic math operation with complex numbers, which would be multiplication of two complex numbers. And hopefully we realize that when two things or two terms are next to each other, we don't have to put a symbol of multiplication. We know that these two numbers are being multiplied. Okay, and in this case, we're multiplying complex numbers. So the way we're going to do this multiplication is the same way that you multiply our basic polynomials. We're going to do FOIL, right? That means that the first term has to be multiplied with both of the terms on the other term, and the second term has to be multiplied with both of the terms of the other term. Okay, so let's go ahead and do that. Let's go ahead and do FOIL with these two complex numbers. So when we do FOIL, we have 1 times 8 is going to give me 8. 1 times a -7i is going to give me a -7i. Then now the second term, positive I times 8 is going to give me a positive 8i. And a positive 8i times a -7i is going to give me a -7i squared. Okay, and I can see that I can combine two like terms. I do have two terms that just have an I. The -7i plus 8i can be combined to have just I. So -7i plus 8i is just I. But I see that the -7 with the I squared, I know the definition of I squared. I squared stands for just -1. So I'm going to replace that I squared with a -1. So now I have a -7 times a -1. That's going to give me a +7. Now I have two constant-like terms. I have the a plus 7, which will give me the 15i. So voila, I I multiply these two complex numbers. The product of these two complex numbers gave me 15 plus I, gave me another complex number. Okay. All right. So let's do this one. Let's go ahead and you see on this one we have a complex number outside that's being multiplied, but this complex number didn't have a real part, and that's not a problem. The inside the parentheses we do have a full complex number, the real with an imaginary, but the solution is easy. On this one, we just have to distribute just the imaginary part to the other complex numbers. So to do this, we're going to multiply 17i times 1, which is going to give me the 17i. 17i times the -7i is going to give me a negative 119i squared. Let's substitute the I squared with what we know what it is. It's a -1. So negative 119 times a -1 gives me a positive 119. Again, do not put this answer on the computer. It'll mark it wrong, okay? Because it's not in standard form. The standard form is always real plus imaginary. So the way we're going to put it in the computer is 119. This is my real part plus the imaginary part, the 17i, okay? Now, so this is in standard form. So then let's do this last piece because I see that I'm running out of time and I want to make sure that I cover all of the basic operations. So the last one is a division. So we're going to divide complex numbers. Now on this one, for this first example, the numerator is not a complex number. It's just a real number, 3. The bottom number, it is a complex number, but it's already simplified, but in order for us to put it in standard form, it always has to be real plus imaginary. So the way you're going to submit this answer, even though there's nothing that to divide, because we cannot divide it, it's already in simplest form, is we're going to do this division, we have to multiply by what's called the conjugate. Now, and it's the conjugate of the denominator. So what is the conjugate of a number? So here, if my number here is 5 minus 6i, the conjugate is going to be the same values, 5 and 6i, but they're going to have a different sign. The conjugate of 5 minus 6i is 5 plus 6i. And this is what we're going to multiply our denominator and numerator by in order for us to simplify it and to put it in standard form. Okay, so let me show you what happens when we multiply the conjugate to our denominator. So again, we're going to multiply the bottom one by our conjugate. And the reason why we want to do it is because we're going to end up canceling our imaginary part on the denominator. But we can't just multiply this 5 plus 6i on the bottom. We have to do the same thing on the top. And this is like if we're multiplying by 1. 5 plus 6i divided by 5 plus 6i is 1. So we're not changing anything, but we're going to multiply across. Okay, so let's go ahead and do this. So when I multiply the top, it's just going to be the 3 times 5 plus 6i. And then the bottom one becomes, again, another FOIL of two complex numbers. But when I do this multiplication, I get 25 plus 30i minus 30i minus 36i squared. I see that the 30i minus 30i, that becomes 0. And then I have 15 plus 18i on the top, and then on the bottom I have 25 minus 36i squared. But what is I squared? I squared is -1. I'm going to replace it and then multiply it. So -1 times the -36 gives me a positive 36. And 25 plus 36, you see that I have a 61. So what I ended up doing was, in the bottom, now I have only a real part. I no longer have an imaginary part. And by me doing this, I can separate this addition on the top into separate fractions. Okay, since they have a common denominator, I can split it up into a real plus imaginary. So the real part would be 15 divided by 61 plus 18 divided by 61i. And now it's in standard form. It's real plus imaginary. Okay, so I still have 5 more minutes, so let's go and do just a different one as far as the solutions. Okay, to write this addition in standard form, or to help us add um, radicals that have a negative. Okay, so again, I have this negative 75, the square root of negative 75, and I have the square root of negative 12. So I know that these two produces imaginary numbers because I can rewrite it and write this negative 1 times 75 and the negative 1 times 12. Okay, so I know that the negative 1 is I squared, and I know that the square root of a square is just going to give me the negative 1, right? But and I'll go ahead and write it. Okay, so I have I square root of 75 plus I square root of 12. Now, you might think maybe it's already simplified, but we need to see this. Okay, 75 can be rewritten as 25 times 3, and 12 can be rewritten as 4 times 3. Now, these are easy to split up, but the reason why I wanted to split these values up is I always want to split them up into perfect squares. 25, the square root of 25, I know that's 5. The square root of 4, I know that's 2, so that simplifies. And this gives me this, 5i square root of 3 plus 2i square root of 3. Now I can add these two because these two terms are the same. They both have a square root of 3. So then to add the radicals is just the outside with the outside. So the final answer, the simplified answer would be 5i plus 7i is 7i. And then just keep what's in common, the square root of 3. Yes? So it's always nice to have the squares. Now, sometimes we don't have squares, and we see, again, the solution here in standard form would be the 0 plus 7i. Okay, let me see if I have a, oh, um, I'm just gonna go ahead and skim through this really quick because this is just one of the things that you're also gonna discover that our answer is no longer gonna be does not exist. So this is a good example where it says use the quadratic formula to solve for the quadratic equation. And again, if I'm using the quadratic formula, just to review, it's here. My a value is 1, my b value is negative 2, and my c value is 2. Okay, if I apply my quadratic formula, okay, you see that we would have ended up with a negative 4. And again, in the past, we would have just said, oh, this has no x-intercepts or the answer does not exist. But we can no longer answer that because now we know about imaginary numbers. Now we need to answer that this problem does not have real solutions, but it does have an imaginary number solution. So again, if we have here, I know that the negative 4 can be split up into the negative 1 times 4. I know that that negative 1 is going to give me outside an I outside the radical, leaving me with just the square root of 4. I know that the square root of 4 is 2. Okay, so this is going to give me 2 plus or minus 2i over 2. So the solution for this problem in standard form is just 1 plus I and 1 minus I. So no longer are we going to be able to just answer does not exist or no solution. Okay, so again, thank you for joining me today. I have two solutions. This is all we have time for today. If you are here with me right now and you want to download my presentation, if you look at your screen here, there's a little box with an arrow pointing down. If you click on it, you would be able to download it. But in case you know of someone who missed it, these will be uploaded to our YouTube channel. Again, I'll pass it back to our presenters. Thank you so much for joining me today.
Thank you, Mr. Carrizales, for your presentation. So yes, we do want to repeat that if you want to download the presentation, go to the top right corner and click on a little box with the arrow going down. And then the previously recorded sessions, which are available on a YouTube playlist, that link was posted on the chat. This session will also be available on that playlist later today. Also linked was a short survey to help us improve our TVE sessions. So please take a few minutes to fill out that survey. And before you all leave, I want to share the TVE sessions that we will have next. So at 1 p.m. today in this room, we will have a presentation So at 1 p.m. today in this room, we will have a presentation by the EPCC Writing Center. We will be back with Happy Math Hour next week at 11 a.m., where Math 1314 will cover finding zeros of polynomial functions, and Math 1324 will cover simple and compound interest annuities. Our 1 p.m. session next week will be a presentation for La Nube, the shape of imagination. Thank you all for coming in today. We hope you all have a lovely weekend, and if you have any questions, feel free to use the chat box or your mic. We hope to see everyone again for Happy Math Hour.